Think very much. Yeah. I prefer to sort of ramble around, so I'll take the walking mic. Yes, so thank you, Lorenzo. It's lovely to be here. This was an event for those guys who were here in the first one. I always wanted to come to the first JanusCon, couldn't make it just due to family obligations. So I was really excited for 2020. Yeah, a lot of things we're all excited for in 2020, and this is so it's thrilling to finally be here and to see everyone. And hopefully this talk will be a little bit educational and enlightening. We're going to go kind of deep into what the actual voice cloning process looks like and what the actual AI audio generation process looks like, and then talk a little about open source things and actual commercial entities that are doing it. But I want you to hopefully to leave here with the idea that you can understand how the theoretical underpinnings of this stuff works. And so if I get to some places, and there's also the chance at some point somebody gets to win the rose. So there's a rose. All right. So just stay tuned for that later. All right. So here we go. So let's just state the obvious real quick. Right now, we're currently living the dream, right? This is a golden age of artificial audio and TTS. People who are using Flight and the early tools are stunned. I know people who have been in the industry for decades who are just agog with the fact that this is progressing as fast as it is. Every couple months, something changes that makes it even better. And I don't know if you guys remember I actually had to take out a couple of these references because I realized that no one knows Star Trek IV: The Voyage Home. Who here knows Star Trek IV: The Voyage Home? Great, that's actually more than I thought, right? So I had a bunch of those jokes in here, and like I just talked a little while ago, a much different version, and I used a lot of them. People were like, "I've never seen that movie," and then I realized how old we actually are. But being able to talk to computers, having them talk to us, that was the dream. That is the dream. And so we're kind of living it. And in our industry, we have these like very, very super duper common use cases, right? This is what we deal with: IVR, support, contact centers, a lot of real-time use cases. And what's interesting is that there are two kinds of AI audio at the moment. There is the kind that works in real time that you can get in sub 500 milliseconds or even at less than a second that does an excellent job. And then there are things that can take minutes or even many minutes. And the difference in quality can be somewhat striking. So one thing I want to get across with this entire talk is simply that there is no one size fits all. Definitely look at the use case you're trying to get to and make sure that you target your audio to that. So we'll keep going. So all it takes to do this, though, is a little bit of AI. So let's talk about it for a sec. So here's kind of a standard model. This is from the Kokwi. I think this is the Your TTS sort of embedding model here. You can see a lot's going on here, right? So there's a lot. Actually, Lorenzo, I don't want to walk out of frame. There's the camera. So those of you who are watching online or in the future, I apologize. I'm going to start walking around, so you're going to lose me for a minute, but just keep listening and I'll come back. So you have a lot going on here, right? This is a fairly complicated architecture for any kind of machine learning system. One thing I wanted to show is that there is the training system on the left here and the inference system on the right. And they're vaguely equivalent. What you're really doing is trying to take a reference waveform, you're putting it into an encoder, you're generating an embedding, and you're basically putting into these layers here. You also have your text input here that you're actually going to be generating into the actual audio and some language ID. And I'm going to show some other examples of other ways that this is done. This is just this style. And again, there's a lot of research going into different ways to do this exact same sort of generation flow. So don't think that there is one correct way to do it. Part of the papers, if you read them, you'll find out are that they are innovating on how to do this exact thing. But the interesting part here, one thing I wanted to cover before we get started is who knows, just to raise your hands, who understands or has worked with embeddings at all? Okay, and tokenization. You guys know, do anyone know what tokens are? Great. So then this is all probably going to be interesting to people, which is awesome. That section down there is very critical, right? How do you take a waveform? How do you take some sort of continuous amount of data like audio and then translate that into something that we can like numerically compute and that can actually be used in machine learning? All of it turns into vectors and linear algebra and math in that regard. But that layer there is critically important. So if we go to what an embedding is, so we're going to make a tangent here to what is an embedding. Let's talk about what word embeddings are. So this is one of my favorite graphics. So this is the way that everything is represented, right? We'll start with words and we'll get to audio data, because audio data is just effectively words that are a lot more dense and a lot faster. But if you think about it, you can encode the idea of a king and a queen and a man and a woman as a vector. And a vector is, just an array of numbers, and it doesn't matter if those of you who know linear algebra, this makes sense. If you don't, it doesn't really matter. You can think of like king as, let's just say that's 0.6 by 0.3, right? So you have two numbers, 0, 6, 0, 3, that's king. And then you have queen, let's just say that's like, 0, what would that be, like 0, 6, 0, 6, right? So two columns of numbers. And then you have the word royal, and royal has its own directionality. So it has like it actually has a negative slope to it. So you're going to have a, 0.5 and has a -1 to 0. Whatever. The whole point is, if you take king and you subtract royal, you should get man. And if you take queen and you subtract woman, you should, so you get queen, subtract royal, you should get woman. And that is how all of it works. It's just adding together the columns of numbers that are vectors, and they represent new meanings. And that's what all of the training of the AI systems do, is link together the meanings of these words by giving them equivalent vector numbers that allow you to figure out what things have relationships. Here's another example of that same thing. So king minus man, you can kind of see how it all goes together. And without having to know a lot of linear algebra, how vector math works or dot products, you can kind of see that is basically how it's done with words today. And that is exactly how they do it as well with audio. Now, what's interesting when you get to the big systems is that this is like a two-dimensional vector, right? We have 2D here, so just two coordinates. When you get to larger systems, like you use the ADA embeddings from OpenAI, you're talking about 1,536 dimensions here. So a much larger dimensionality, which is great because you can capture a lot more information in that dimensionality, right? 2D doesn't give you that much with just two numbers, but you can capture a lot more when you go into the thousands. So you can kind of see, if you can imagine in your brain just all these dimensions spinning out, and you're putting like dots and points and lines everywhere, how much you could capture. And so you can see studying, institution, these things all kind of bleed together. So it is important, though, that the system works on the basis of tokens. And tokens are a way of representing words and sounds or anything else in a more efficient format so that we can actually like computationally get to them. So what is a token? So the idea of a tokenizer, this is a great one. And I got this from Assembly AI. They have a great sort of article and series of papers on this. Multidisciplinary, you tokenize it, you get 3 separate tokens out of that, right? You wonder why you submit things to OpenAI or anywhere else, and you have to pay more per token, because multidisciplinary actually has 3 independent parts that are very, very important. What it does is you're taking stem words. The tokenizer knows how to take the stems of things and then add endings or prefaces that change the meaning of it. And so you can then represent very, very, very large language models or anything else by having a smaller corpus of things that you actually tie together. And that is why when you're using OpenAI or any of the LLM tools now, you'll see it generating it like a little bit at a time. Because what it's actually doing is predicting the next token in the sequence based on the probability of that being the correct answer based on its training. So you'll see it being like jumping, singing. It does all of that sort of in a row. It just kind of tacks them on all in a row. You're not getting whole words. You're getting pieces of words at a time. So it gives you, and it basically changes it for those of you who know, big O notation. You get from like two N words to, N+1 tokens. So it's much more computationally efficient. The question is, how does that work with audio? Because audio is not words. Well, audio density is much, much higher. So we're going, embrace the large language model here. Tries to go from embrace the, to embrace the unknown. That's the next one. You can do the same thing effectively with audio, because all you're trying to do is predict the next audio token. If you think of audio in terms of that way, by tokenizing speech, you can say, oh, what would be the next effective token in this chain? You do that with, and it's cutting off a little bit in the bottom here, but there's 2 kind of ways to do this, right? The problem with sound, as we all know, is that it's not just words. The density of language is so much higher. In fact, I think it's something like, it's orders of magnitude higher. It might be 50 or a little bit higher in terms like per second, maybe 500. Anyway, language, much higher. Also, a lot more information encoded in it, right? There's timbre, there's emotion, there's prosody. There's all kinds of things you need to capture that aren't there in the written word. So how do you do that? Well, you can't just use the typical tokenization mechanisms that they use for text. You have to do more. So what you want to do is pull out semantic tokens. So we're talking, they have basically two different ways. You can use there's a BERT one. These are all, again, research papers you can go look up, but they use a semantic token extraction where it says like, what am I actually saying? What are the words? What is the content of what I'm saying? And then you have the acoustic tokens. How am I saying it? What's the speech pattern? What's the long-term coupling of how I'm doing it to my presentation style? Because language also, as a continuous domain, has the idea that I have what I'm saying, the content-wise, but I also have long-ranging effects where something I'm talking about now affects the future. It's not just a discrete system, it's a continuous system. So let's just keep going here. Blah, blah, blah. Hopefully this is somewhat interesting already. I know it's early, so I feel like this is what I feel like in my own head. So what are we doing with the new generative AI systems? Well, there's a lot of different ways to do this. Right now, this is kind of the way that it is done with generative AI, is taking the text, you put it through a phoneme encoder to make sure you get the analysis of that. You can do the duration pitch predictor. You then pump that into basically a diffusion model. The diffusion models are sort of the generative version of how you can make the audio sound sort of more human in that way. They have trained it on many, many different speakers from around the world to basically have that giant vector space like we were talking about that actually encodes a lot of the information that you need there, and then you basically have to decode it into real speech. There are other more advanced ways now they're coming out with as well. So, like I said, you're going to have to start separating out speech, different sections of speech, and how you capture them. So you have like emotion encoders now. You're having content, text encoders. You're having all kinds of different ways that you can capture information in audio to then relay it back. So you're going to see coming out soon, and this is a lot of the current research going into it, is how do you really capture long form intent and long duration information about speech. I know we've been talking to some actors in Los Angeles, and these are famous people who are very interested in the idea of them living forever via their voice. But they're also very, very cautious. They know that when they read, when they read a script or when they read a piece of text, that they have an emotional through line throughout the whole thing. They read the entire thing first, they identify points that they want to hit, and then they craft the way they tell the story specifically for a given piece of text. And so they're nervous and cautious because they feel like the artificial voices that we do lack that. They lack that ability to do storytelling in that way. And we've been talking to them and working with them a lot on the idea that we could actually figure that out from the way that you tell stories by analyzing the stories and the way that you tell them and how you tell them. And that is coming soon. So you really could have a voice that resonates with what you feel like is true about a story. And everyone talks about the fear of this and the ethical concerns and things like that. But I'm here to tell you also there's a lot of excitement about the idea that these people could really, live forever and keep providing for their families and or have an impact in the future. And they are passionate about it, but they want to make sure that it's good. And the developments in the last couple of years have really proven that we can get there relatively soon. So we're almost there, right? We're almost at the hello computer stage, which is great. All right, so let's get back to this. All right, so let's get back to some actual real practical stuff. So we know if you use AI, you're using a lot of different tools, right? You're using LLM gateways, you're using vector databases, a lot of different things here. Who is actually actively using AI in their companies right now? Great. Okay, cool. So a lot of this stuff you might know all these tools or how to use it. And we'll focus on the TTS section of this stuff, right? So I pulled these numbers from Dave Horton of the Jambones Project. He's got a great blog out about this. So thank you, Dave, for doing this because it was a ton of work. Go to that website to get a much, much more in-depth version of this. But these are time to first byte from a lot of the commercial providers, right? You have ElevenLabs is the big boy in terms of just I think Mindshare, and these are just four of the. He also put Google and Microsoft on there, but I think we all know about them. Interestingly enough, I think Dave points out rightly that Play.HT, while having a 92 millisecond time to first byte, actually has quite a bit of silence padding. So one of the things you want to take away from this really is that there are a couple other factors besides just how fast can I get the audio. Play.HT is great. Eleven has excellent text pre-processing. So I kind of gave these random grades. These are just grades that I gave them. And that is based on having used all of these and determined that when you feed them information in text, do they say it correctly? Do they say numbers right? Do they expand on acronyms correctly? Play.HT has probably the weakest system in that regard. You have to really pre-process your own text quite heavily, expanding numbers and variables and anything like that to actually make sense. OpenAI does a good job. It has a limited number of voices. DeepGram's new stuff is pretty good. It's just not my favorite. 11 is probably the best so far. And but they're there. They're there and you can use them today. And a number of these have WebSocket interfaces that are pretty great. So if you're not using them, you should. But then again, also not everyone's going to make it. So the Koqui project, if you know who they are, they were an early, that was that first graph I showed you, was the Your TTS, came from the Koqui guys. They've been a long-running TTS project, and as of 3 months ago, they had to turn it off because the space is getting so competitive. We work in RTC, a lot of times we work in traditional telephony in a very commoditized market, which is a very difficult market to work in. The margins can be low on some of the products, and it is hard. And generating new language or voice models is very, very expensive. And that is basically what the guys said. They could not keep up with the current pace of innovation because it's just too expensive. So you look at a lot of things that are going on out there and a lot of the papers that are coming out to make it easier and faster, more efficient to do this. But you also are going to see, folks, things are changing so quick. People who have been around for a long time will not be around. So make sure as a developer, you don't couple your system too tightly to one company or to one project because it is rapidly changing so much. And this affected quite a lot of people, the Koqui TTS going down. But here are some open source ones you can use. If you want to do it yourself, I know people here are very DIY-y. This is kind of the OG one that came out that kind of kickstarted a lot of this. Play.HT was originally based on this project, and they have since gotten a lot more sophisticated. But a guy named James Bedecker developed this. James Bedecker is a homespun AI guy. He did it all himself, just in his garage, in his house, with a bunch of GPU cards, trained his own language model. He now works for OpenAI, of course. And this, originally, they called it Tortoise because it ran at 20 to 30x real time, right? You couldn't use it for real-time analysis, but it was very, very high quality. They've gotten that down now, right? People have worked on this project. This happens very, very fast these days, down to about 0.2 to 0.3x real time. So you actually can use Tortoise these days to generate audio for real-time scenarios. These are, much as Janus and Camelio and other projects, these are occasionally non-trivial to set up originally and get running in a distributed mode and in a high availability environment. So take that with a grain of salt if you want to run your own versus using a commercial one. Again, I always tell people to validate their ideas, maybe the commercial product, knowing that they can always fall back to one of these if they need to. And this one actually has an interesting point here on the cloning process. The zero-shot cloning of this one, you need a couple minutes of audio to kind of train it, right? So going back to the diffusion and the model I was talking about earlier about how this all works, the way that zero-shot cloning is, I give you a small sample of my voice, and you can replicate me by taking my voice, translating it quickly into one of those embeddings, such as a giant column of numbers, of a vector, and then putting that into your model so that my voice is represented by weights and things you've already trained. So they, for Tortoise, can do that well, but they need a little bit more audio. These guys, Open Voice, from MIT and they specialize primarily in color tone transfer. So you also are now getting into the idea of voice dubbing, if you've seen that, where my voice can speak in many languages. I can speak in Japanese or Mandarin or Russian. And that is another transference process based on that sort of training model. This one is an open source one that specializes in that color tone transfer. So I can take an existing piece of audio and then actually make it really happy or make it really sad or whatever you want to do. That's not available in all these things. A lot of dials you can twist. Open Voice is pretty great. Only needs 2 to 5 seconds of training data, although I have found that using more really helps. This is kind of how their flow works. This is what they put out in their paper of how they did it. So again, like they are taking kind of the same thing as we saw before, right? Text content goes into something that extracts accent, emotion, intonation. You can kind of encode that in the text. They have their base speaker TTS model. That is the diffusion model. But then they have a tone color extractor. That was the thing they sort of wanted to hang their hat on, was the idea that if you extract the tone and color out of the audio waveform, you can actually then inform the data and make it quite a bit better. VoiceCraft is probably the newest one. Again, this is about a month and a half old. Again, it's changing very fast, so you got to keep up. This is the newest one. Takes about 5 seconds. Reference audio is not quite yet real time. It's getting there quickly. I would not be surprised if this has real time within the next 6 months. Excellent quality. Really one of the best voice cloning tools and audio synthesis tools that I've seen. Really commercial grade level stuff and easy to set up, already has Docker containers ready to go. So if you're looking for something to play with, I would highly recommend checking out VoiceCraft. And I believe it supports a number of languages. Again, language support is a big one as well, depending on what you need. English is generally the one that is the number one. So we'll just real quick, but again, with all these tools, you're going to have a problem occasionally with bad audio. So we all have seen AIs hallucinate and put out really weird text. They can also put out weird audio if you haven't seen it, you know. And I asked Lorenzo, they unfortunately don't have the audio here, but it'll sound something like, there's a couple different versions, right? There's one where you can have them talking like this, and then and then goes back into it. So you'll have weird gaps like that. Or they'll be talking, and then back to normal again. Question is, how do you detect that, right? You're using this and you need to know, is the audio bad or not? Well, there's a couple ways to do it, and I'll just go through these real quick. There's two main issues: wrong, unintelligible words, and significant pauses and strange noises. Those are the two big ones. How do you do it? Well, you can look at the waveform. So this is where the Rose system comes in. This one or the next one? Let's do this one. Who can spot, okay, you can kind of see the time codes there at the top. Who can spot where the bad section of this is? What's the bad section? Anybody? Shout out a number. If you can see read the number, they're hard to read the numbers at the top. There you go. All right, great. Okay. I don't even know if that's correct, but you get a rose anyway, Mark. Here you go. Congratulations. Yes, so the bad sections, there's actually two bad sections in here, and it actually, and if you were cheating, they're right there at 1950. So right here, right, that's the bad section right there. So there was a hint on the screen. That's the bad, and it doesn't look that bad from a waveform, right? You're looking at it, you're like, you can kind of see it looks a little bit different. It does help when you turn it into a spectrogram. You can really start to see, oh, okay, so there's something there that doesn't look like anything else, and that's probably not good. So what do we do, right? How do you detect that? You know, detecting anomalies in continuous data series is very difficult. There's research that goes into this. It's very, very hard. Well, you can kind of short circuit it. If you're a guy like me that just needs to solve the problem, what you can do is you can train vision AI on the spectrographic data. So you just chop it up into good and bad bits, get a whole bunch of examples of these, and you go use, I put nickel on here because a good friend of mine runs that AI company, but you just train a vision AI system to determine, based on the spectrographic picture, what is good and what is bad. And doing a spectrogram is very, very efficient in terms of computational power, and you just put it through one of these systems, and it works shockingly well. It can find bad audio very, very quickly. On the order, this is again a thing you probably wouldn't do in a real-time context, but if you're generating audio for anything and you have a little bit of extra time, using Vision AI to determine from this or waveforms is a great way to do it. You do have to kind of train it yourself, but it doesn't take that much. Here's another one from ElevenLabs. It was a bad one. They have a couple dialing settings where you can kind of turn up the emotionality of things. And this one's a little bit harder, which is why, Mark, you got the rose on the previous one, because determining the bad one here is a lot trickier. It's not where you think it is. It's right there. That's the bad audio. And it looks like everything else. And if I could play it for you, if you want to hear it later, it does just sound like he switches into a different language for a couple seconds and then goes back. Well, then how do you determine that one, right? Again, the spectrogram does give you clearly part of it, but actually the first section of that is also all bad. So that entire block there is not good. So you could say, okay, well, you know, we're going to regenerate. And what you do effectively if you have bad audio is just regenerate that segment again, right? And if it has bad audio again and again and again, it's probably a bad input. But if you regenerate a couple times and you get something good out of it, and then the spectrogram looks fine, then you're probably okay. But if the spectrogram looks okay and the waveform looks okay, you can't use the vision tools to do it, or you can use them a little bit. What you can do, because that part is still bad in there, that part's all gross, you can use something like whisper timestamps. So what you're doing effectively is going back again to a speech to text. So you take what you just generated, slam that through a speech to text system that gives you word level timestamps with a confidence, and you specify the language you need. Again, Whisper is great because it has such a large corpus of languages available. Very, very, very fast to do this. And then you just check out the confidence of that section or of the entire phrase. And usually the confidence levels for any given phrase will be in the 70s, 80s, or 90s. You start getting in the 20s, 30s, 40s, you realize that you probably might have a problem with that section. Again, you're regenerated quickly. You check the new one, make sure it is or isn't equally bad, and then move forward. These are techniques that unfortunately can't be used, like I said, in like a real-time scenario. It's very, very hard to do this. They might be soon, and these are incorporated, I think, into some of the generation pipelines that are coming out, where they'll auto do this for you, and if the audio is not that good. It also depends how you generate audio. If you're generating it at short little bursts at a time versus, you know, whole paragraphs, there are ways to chunkify and make sure that you're actually being able to generate the same thing over and over again. I think VoiceCraft allows you actually, one of the big things they wanted to do was allow you to edit sections of the generated text as well in real time and only regenerate the portions that you want. So again, using this, you can actually regenerate time codes specifically versus having to regenerate the entire thing. But yeah, that kind of wraps it up, you guys. I just wanted, hopefully, that, you know, everybody can know a little bit more about how this stuff is done. Some of the tools that are out there. If you have any questions about AI or generated audio like that, I'd love to talk more about it here or later. Thank you all for waking up and getting here. And yeah, I hope have a great day.
Oh, thanks, Evan. This was really great. So, do we have any questions for Evan?
Is there any way to stop it? Like, is this an inevitable thing? It's just going to happen.
Yes. It's inevitable. It's. I was at a talk from, this is, God, it's got to be 4 or 5 years ago now. There was the ex-head of DARPA was talking in LA, and so we went to hear her talk, and the idea of voice cloning came up, and you know, people in the room were very interested in the idea of it being used for fraud, which it already currently is. People are, you know, there was a big theft in Australia recently of bank money. Somebody, you know, they cloned someone's voice and got a bunch of money out of people. And I think it was James Vanderbeek or something like that was in the audience. And I remember asking a question, being like, well, this is coming anyway. What are you going to do? And I think James Vanderbeek was like, don't take my money. Like, stop taking my money as an actor. And I was like, man, it's not about that. It's about the fact that in the future, anyone will be indistinguishable from their virtual selves. And that we have to sort of adapt to it the way we adapted, like with Photoshop, where you see digital pictures and or are shown them, and you just know that very likely something has been altered. And I think that when it comes to audio and media in general in the future, you'll just have to assume that the things that you're seeing without first-party attestation, whether you saw it or someone you know saw it personally, that potentially what you're seeing is not real. And I think we, as a generation, and I'm talking like, you know, 20s to 70s, are going to have to grapple with that a lot more than our children. And I see my 10-year-old and 7-year-old or 8-year-old now who are much more aware of the kind of manipulation that's happening, and they still fall for it, but they are comfortable with the idea that what they're looking at and hearing might not be the original source of truth. And it's a big societal shift. And, you know, I hope you all have safe words with your grandparents.
Any other questions?
Interested in, it seems like you know the technology. Singing is the next one. Do you have any?
Oh, yeah.
Do you know how that's going to be modeled, or what tools need to do to extract tone and that sort of thing.
Oh God, I'm so glad you asked. Hold on, I can't turn the audio on here. I actually used one of those tools, the Sonu SNOSONU, to generate a Janis Khan like theme song, and it's an Italian ballad about Janis Khan that I put in there. Yeah, for music it'll be very similar, right? Music, sound effects, anything sort of audio in that regard is all being trained, and the music systems are being trained on the same sort of data, right? It's just the. I was having this conversation last night as well. That is, there's so much to encode that is sonically complex in music that they are taking some shortcuts right now where they're probably just doing specific genres at a time. I can't generate like a reggaeton country Italian ballad. It's just too much, right? There's too much information in there at the moment to basically be computationally effective, but that is rapidly decreasing, right? One of the big advances in the Transformers paper that came out a long time ago that made a lot of this possible was the way to make all of this faster to do on GPUs. So music is coming. I would expect pretty soon here, probably within the next, I give it like, I mean, you can do it now, but within the next year or so, you're going to see some pretty great open source music and sound effect generating things. And at the end of the day, it's all about the library behind them and finding the copyright and the music and that kind of stuff. So yeah, it's a fun time.
Great stuff. In your experience, do you see this voice cloning to be used as a basis for voice identification and all that, like voice biometric?
Yeah. So actually, it's the voice biometry is a real problem, right? Because it can easily confuse those systems. So I would actually steer pretty far away from the idea of using voice as a biometric identifier without some other two-factor authentication behind it. These systems are too good these days that they can fool the ones that I've seen, at least. But I would also like to point out that like one of the nice things about all of this is that people who do have the voice cloning, and I work a lot now with authors and folks who are cloning their own voices within articles. There is emerging evidence and things that we're looking at where the way someone speaks is actually more tightly coupled to the way they write than you might think. So there are somewhat unknown identifiers in that. So there are other biometry systems and signals that are going to emerge out of this that aren't just pure speech patterns and vocal data.
Any more questions for Redman?
How reliable are these systems by now? You mentioned that the AI-generated voices, they are making mistakes, of course, and they're going super weird for a few seconds. How often does that happen? Is it like once a minute, once every 1,000 words? Can you quantify it somehow?
Absolutely. It's actually quite stable, and they're quite efficient and quite well done. If you don't dial up some of the weights that cause them to have style exaggerations. So in all of these things, you can basically put in the amount of diffusion or generation you want, like noise you want to put into the actual diffusion model in the back end. When you're using ElevenLabs, that's all you're doing. When you're like sliding sliders around, you're just turning up how much like noise you want to put in there. If you dial them up too much, that's when it goes crazy, right? And what that's doing a lot of the times is basically it's causing it to look like, imagine again, you're in that giant dimensional latent space of like all the voices, and they've trained their language model on 20, 30 languages. And so what you're saying is somewhat close to maybe something in a different language. And if you dial that way too high up, it's just going to go, the vectors are just going to go in the wrong direction. So as long as you keep that somewhat stable and somewhat like confined, it's very, very, very reliable. I would say, I think out of tens of thousands of hours, it's really been like, 50 to 100 examples of it having a wrong thing. So really not something to worry about too much. And if you dial it all like pretty far down, it almost never happens. What you lose is a little bit of that emotion, a little bit of that actual like real like intensity of a human. Again, use case dependent. But if you're looking for style or exaggeration, you're trying to dial it way up, that's when you start to have some real issues. But people like that. They like the sort of the ability to have more emotion. And again, a lot of these voice cloning tools, you might have to do several voices. You might, they even with the ability to change the emotional resonance, the tone frequency, or anything else you want to do, they really do sound like the way they're originally recorded. If you give me like a talk of me doing this versus me being really happy and telling at a party and whatever else, man. Like it's gonna like you can't make me sound like this, like and be like totally rad, dude. Like it's really hard to make it do that artificially. You have to have multiple samples and multiple different clones of a voice to do that at the moment. But that's some of the research they're working on is how to do that kind of style transfer from. Hopefully you all can be surfer dudes one day.
One last one. Why not using voice detection, like voice to text,
Yeah.
to detect the issues?
Voice to text.
Voice to text or voice detection.
So that was the last one. My slides are off, but that was the last one I was showing you. That whisper timestamped is voice to text. It's exactly what it is. So the vision analysis one is one where it's a very, very fast way to do it and detects as like a certain classification of problem. But the voice to text one is another way to look at it. Again, you have to get the confidence out of it because again, you voice to text, you don't know what the text originally was necessarily, right? You just want to know, is there a problem with generated audio? And you have to figure out how to compare that. You can't compare it against the original text, but sometimes you don't have access to it. You just have the audio file. So how do you do it apropos of nothing? Voice to text, check the confidence of it, like, yep, this is a low confidence section, regenerate that section again.
Quick question. We've had basically intelligible, understandable speech for decades now.
Right.
This is making it cooler and fun, but it's honestly, for telecom, it's just a feature. Oh, it's a little more natural.
Mhm.
Are you focused on new entertainment cases or content creation cases personally? Or I'm just like,
Yeah.
comment on where you can actually make money on all this improvement, because it is very expensive.
Absolutely, it is expensive to do. So there's two main use cases. In a telecom use case, the money is to be made is in effectively the initial ones I was talking about: contact center, IVR analysis. So a good example on that is, I know there are large companies like AAA in the U.S., right? There are car service, airlines are using a lot of these technologies to effectively make customers less angry when they call. A lot of the calls are people in trouble or upset or trying to figure something out. The natural sounding voices have shown to reduce their anxiety and then get them to an agent or their solution faster. So not only does it decrease the money on their side spent on the phone, but they're willing to pay more for it because the customer satisfaction goes up. So money has been made there by making it feel more natural. Again, people in this room understand a lot of this technology or how we're doing it. The general populace, the average person, does not care about any of this. They just want their problem solved today. I think about it a lot like Star Trek, right? Where they have to ask the computer something, they want an answer, and they want to move on with their lives. So in our world, that is the place I've seen you can make money. The other places you can do it are absolutely places where you have the ability to render large sections of text. So yeah, entertainment, anything where people need an audio version of something, and they generally will pay for that because, again, they don't have a particular interest in doing it themselves, and even copying and pasting the websites is too hard. So workflow enablement in that way is kind of a big name of the game.
So one comment/question for you. One interesting field of application of these technologies, I think you know something about this, is in the phishing area, so voice phishing, basically.
Yeah.
There are people who are making their business out of this. So I don't know if you have any experience with that. Companies like Rachel Tobac's social engineering company who is doing exactly that.
Yeah.
And then just a side comment, congrats on your presentation. It looks like you trained as an actor, so this was perfect presentation for someone who is trying to also highlight the differences in tone and things like that, so great. The only issue for the non-English speakers here is that we will have to replay your recording at 0.75 the original speed, because it was really hard to follow. It was perfect English, obviously, but really fast. So we will have to try some audio mangling on your recording. I will let you know.
If I can leave you wanting more, then I've succeeded. So if I have to make you come watch me again, such a shame.
Now, for people like us who are used to the IETF, there is just one person who is faster than you, who is known to be Ekar, E-K-R.
Oh, yeah.
Yeah, I will send a sample to you. You will enjoy it.
Well, Now I have now I have competition. Thank you.
Oh, thank you, Evan. Thanks a lot.
Okay, everybody.